I'm going to introduce a general class of temporal network that are suited for empirical application. That is a work based, a joint work with Oliver Williams, Fabrizio Lillo, and Vito Latora. But the work is based, I mean, the background of the work is based on some other papers that I collaborate with Carlo Campaiola and Daniele Tantali. So this presentation is like a sum of some work that we did together. Okay, let's start from some motivation. Many socioeconomic, biological, man-made systems can be described mathematically as networks, and moreover, such networks are inherently dynamic with the link switching on and off. For empirical networks, typically, okay, we have possibly a lot of research questions, but two main questions are about understanding the generative mechanism that give rise to the evolution of the network that are typically used to make prediction. The other point is that studying other kind of process that take place over the network itself during the evolution, like diffusion, like epidemics, let's say, contagion, systemic risk in finance, different kind of process of this type. In such a context, null models are key because they allow to describe the networks as a random variable, satisfying a number of constraints related to the information that we want to impose to our model. And depending on these, let's say, null models, we can use the null models to make prediction in the sense that we create a model by imposing some information. I want to understand if the information that we are imposing is predictive for other metrics. This is the idea of prediction with null models of temporal networks. And the other kind of application is try to understand, to characterize the process that take place over the network as a function of the constraint of the information that characterizes the model itself. So the scope of the paper is to introduce a general class of model of temporal networks which allow to precisely control the autocorrelation of link dynamics that is related to the self-interaction of links, let's say, and the cross-correlations that are related to the cross-interaction between links. Our approach moves from the concept of maximum entropy distribution of network that is popularized by Park and Newman, a famous work of Park and Newman, to introduce, let's say, a new class of models that are based on discrete autoregressive process that are indeed equivalent to the maximum entropy distribution of temporal network. And the methodology allows to study analytically, let's say, some process like diffusion over temporal network, to infer the generative mechanism of link dynamics by using maximum likelihood estimation method, a very simple method to estimate the model on data and to use the model on data. And also, let's say, this kind of approach is suitable for generalization, for example, to account for time-varying parameter to capture non-stationary pattern in empirical data. And to the best of my knowledge, this is the only model, class of model that allow to do this. Okay, what are the preliminary of the work? Why statistical mechanics of networks? Because Park and Newman in 2004 introduced a general class of model of static network named exponential random graph. And the typical scenario to create a model, a null model of network is that we have, let's say, we observe some statistics of the network, like the number of links, the degree of the node, whatever. And the typical idea is that we want to create a model network that has the same or similar value for these statistics. So the statistics, the network statistics, represent the information that we want to impose in a model. And what is a possibility? What is a possible solution to create a model? The possible solution is, okay, assume to have a space G of graph that is called ensemble. We have this S hat that are some observation about the statistics, and we want to find what is the probability distribution of a given graph. So the graph is a random variable. We want to describe a probability distribution. How to find this probability distribution is the probability distribution that maximizes the Gibbs entropy. Why this choice? Because this is, let's say, the best choice in the sense that if we maximize the Gibbs entropy, we obtain a probability distribution for a graph that match the observation, the statistics that we want to impose, but it is maximally random for any other statistics without imposing any spurious constraint, let's say, in the probability distribution. How we can solve this? This is a maximization problem for the Gibbs entropy. That is, we maximize the Gibbs entropy by using the method of Lagrange multiplier, alpha and theta. That is, to impose the constraint about the normalization of the probability distribution, and the other constraint about the information that the statistics computed according to the probability distribution for graph need to match, let's say on average, the observation, or in general the information that we want to impose to this model. Okay, what is the solution? The solution is this class of exponential random graph. Instead of we describe the graph as an adjacency matrix that is a square matrix in dimension n times n, where n is the number of nodes. This is, let's say, the probability distribution is of exponential form, with theta that are the Lagrange multiplier, the statistics that we want to impose, this is the exponential factor, and z is the partition function that is the normalizing constant. So this is a very general class of model that any times that we impose a different statistics, we obtain a different model. Just to have some example, if we have a network that is binary, that is the adjacency matrix, encode also 1 and 0, 1 if a link is present, 0 otherwise. And if we impose as statistics the total number of links, this is we obtain the well-known Erdos-Shreni model. If we impose the degree, that is the sum over the row, we have the case that is why we call statistical mechanics of networks. If the network is binary, we obtain the so-called fermionic graph, because the free energy of the model is the one of the Fermi-Dirac statistics. If the network is weighted, that is a link is a real number larger than 0, in general we obtain the bosonic graph because the free energy of the model will be that one of the Bose-Einstein distribution. Okay, the fermionic graph that are very famous, let's say in many fields, are called also beta model in statistics, fitness model in physics also. This model has been discovered many, many times, depending on the research field we are going to look. Okay, what is the intuition? The intuition is that, okay, how to generalize this for temporal network? A temporal network is a network that evolves in time, that can be described, if we describe the network at discrete time, as a sequence of graph, or in other words, as a time series of adjacency matrices. How to generalize this model to the temporal case? This approach has been introduced by this paper of Van Neck et al. Of 2010, in which the main idea is the same. Let's say the idea is the same. We have exponential random graph. We maximize the entropy, but now instead of using some statistics that depends only on the adjacency matrix at a given time, we impose some statistics that involve two subsequent adjacency matrix at a different time. Okay, that is, the statistics depend on the network at time t and the past network at time t-1. Potentially also, if we want to impose some non-Markovian memory, also past observation. Okay, so and again we can compute. I mean, if we need to define the model, we need to compute the partition function. If we can do this, we obtain a model for a time series of network, a time series of temporal network. Okay, just for example, some example, very basics. That is, if, for example, one famous, let's say, one very used statistics, and then I'm going to tell you why, is the so-called link persistence that is correlated to the autocorrelation of links. That is this matrix. Another possibility is to include the link transitivity. Okay, this is the persistence of link or no link over time. The other possibility is links transitivity. That is, if I observe a link ij at time t-1, this increases the probability of observing another link ik at the next time. Okay, this is related to cross-correlation lagged in time. Okay, what are the drawbacks of this approach? The drawback is that the partition function usually is very complicated to compute and usually untractable. And we have just, let's say, some analytical tractability only for few metrics like link persistence. And the other problem is that in this kind of approach, I mean, the estimation method to apply the model to data are based on some MCMC, that is Monte Carlo Markov chain estimation method, that is a methodology for estimation that is usually very computationally expensive. That is to overcome the problem of estimation of data in a more efficient way, and also the problem of generalize, let's say, the model with, let's say, a lot of metrics, or a lot of statistics, or more statistics, or model more general. We can do this by overcome this problem in this way. That are the topic, let's say, the result of our paper. And at some point in 1978 has been introduced in time series analysis this process that is called the discrete autoregressive process of order P. That is a process for binary random variable X. And the main idea, this is the generalization for binary data of the standard autoregression in time series analysis, for the one that know about this. The idea is very simple. That is, the binary random variable X is, let's say, the model describes the persistence pattern associated with the mechanism of copying from the past. How to model this? We have, let's say, a Bernoulli random variable Q, that is a variable taking value in 0, 1, that according to a given probability Q, we decide at any time if, with probability Q, we copy the variable from the past, the same variable X at some past lag defined by another random variable Z that pick integer value from 1 to P, where P is the non-Markovian memory, the order of the non-Markovian memory. So we copy from the past with probability Q, otherwise with probability 1 minus Q, we sample the random variable according to some Bernoulli marginal. Okay, this is a very simple process for binary data, for binary random variable. How we can apply this? Why we apply this in our methodology to describe time series of network, temporal network? Because, okay, in a first paper of 2020, we model link persistence in the interbank market with the simple DAR1 process for the adjacency matrix, where the link L is a copy from the past, the previous past times t minus 1 with a given probability Q. Otherwise, we sample according to some marginal model. And we do this in an independent way for each link. Okay, so the dynamics of each link is independent from the other. This is in our first paper, and we prove that this is useful in the interbank market to capture some generative mechanism of link in the interbank market. Then in a second paper of 2020, again, we introduced the generalization of this model, the vector generalization, where now the link L at time t can be a copy from the past, again with the same mechanism, but now we can decide, according to another variable L, if copy the link itself with a given probability or copying another link. So in this generalization, vector DAR generalization, we introduce also cross interaction between different links, but the model is Markovian. Now, and another crucial result, in this paper of 2021 by Campaiola et al. And myself, we prove the equivalence between the temporal exponential random graph, okay, the model obtained for with the principle of maximizing the entropy for two specific statistics that are the link persistence and the transitivity, so autocorrelation and cross-correlation, with the vector DAR model, under some parametric restriction of imposing positive auto and cross-correlation. So once that we have this result, the main idea is that we can use the maximum entropy model or the time series model in discrete time in discrete time to model, let's say, the statistical mechanics of temporal network. And by leveraging over this work, we just generalize the model for temporal network, this class of model that is called discrete autoregressive network model, VDRP, by introducing also the non-Markovian memory. This is, again, exactly the same, the model that we described. And importantly, we have, okay, the variable Z that controls for the order of non-Markovian memory, that decide what are the path lag to copy. Then we have Q and L that control for both the autocorrelation and the cross-correlation of link. We impose some, let's say, backbone that is only a subset of link can interact to deal with the sparsity of empirical network. And then we have a Bernoulli marginal that could be, let's say, the static model like Erdős-Rényi, fermionic graph, or in general, whatever. And indeed, we introduce, let's say, both. We study both homogeneous by considering global parameter or heterogeneous, so not specific parameter network. Why this is useful? Because we can solve a number of problems. One, for example, we can study the diffusion over a temporal network in the case of homogeneous graph, that is just global parameter for the memory, the Erdős-Rényi model as a marginal, okay? And in this simplified version of this model, we study the time to equilibrium of a diffusion in a temporal network. What is our finding? What are our findings? Okay, that are summarized in this plot, but just I give you the intuition for a matter of time. That is, the order P of the memory has a non-trivial impact because there exists a P that is not zero, not infinite, in such a way that the time to equilibrium of the diffusion is maximum. The correlation parameter, that is the crucial parameter, is very important because if we increase the correlation parameter, we increase the cross correlation, and at the same time, because of the parameterization of the coupling matrix, we decrease the autocorrelation. And what we have is that we decrease also the time to diffusion. So cross correlation in temporal network speed up the diffusion process over the network. And okay, we have that depending on the diffusion speed, the larger is the diffusion speed, the smaller is the time. This is trivial. Another possibility is that, we can use this model, apply to data to make prediction. The interesting, let's say, feature of this model is that there exists an estimation methodology that is based on maximum likelihood method, very simple, that we can estimate the model on data to make prediction, let's say. For example, we can do this for homogeneous or heterogeneous network, for constant or time-varying parameter. And what we find is that indeed, if we use the football dataset in which the node are the players and the links are the contact between players, and a ROC curve that is a method to evaluate the performance, the important point is that the higher is the curve, the better is the forecast. The main point, for example, in the football network is that if we compare the red or the blue line that are the model with cross correlation with respect to the black line, we have a great increase of the forecasting performance. So we end up with the fact that in cross interaction pattern for this data set, for example, is crucial for prediction. And the other point is that our model predicts exponential decaying inter-event time distribution. This is a limitation because in empirical temporal network, the typical inter-event time, that is when a link disappears and then appear again, the distribution is typically fat-tailed, that is power law. So this is a limitation that is, let's say, a possibility for the improvement of our approach. So thank you very much for the attention.
Okay, we thank the speaker. There are questions?
In the theory of Park and Newman, the number of constraints is equal to the number of nodes or links, I don't know. So you
the
can
number
put
of constraints is equal to the number of
nodes or links in the networks, no? But then you show an example where it is 1, so the total number of links. So which is the extreme freedom, no, in the choice of the number of constraints? Do you see a difference in the various?
Very briefly, then we can, I mean, the point is this. I mean, for example, in the case of studying diffusion, it's very crucial to have a few number of parameters, so a few number of constraints, because you want to study diffusion as a function of a specific pattern of network, like memory. So you have one parameter, and you change that parameter, and you look, for example, at the diffusion. So for the analytical approach of diffusion, it's very important to maintain a few number of parameters. The point is that when you apply to data, it's better to have a heterogeneous network. So in this case, you have one constraint, for example, for each node. So for example, one memory parameter, one, let's say, link probability parameter for the marginal, let's say. In that case, the point is that the model is more suitable for empirical data because it's more flexible. The drawback is that the larger is the number of parameters, let's say, the worse is the estimation, the larger is the estimation error, typically in empirical data. So usually you always deal with a trade-off between, let's say, flexible model but larger estimation error, or less flexible but smaller estimation error. Depends on the task. But I mean, this is the two crucial point with the number of parameters, let's say, that you impose.
Okay, we thank again